Body Control Module, BCM, Automotive Body Control Modules, Roles, Functions, and Evolutionary History 1. Introduction. The Body Control Module, BCM, is a cornerstone of the electrical and electronic EE architecture in modern vehicles. While the BCM does not directly control the engine or active safety systems like emergency braking or airbags, it manages nearly all functions related to the vehicle body, passenger comfort, and driver-vehicle interaction. In popular modern models such as the Toyota Camry, Honda Accord, Ford Focus, Hyundai Tucson, Kia Sportage, and Mazda CX-30, the BCM's role has expanded and become increasingly complex. It acts as the central nervous system, coordinating body electronics to ensure smoother, safer, and more energy-efficient operation. In an era where vehicles are becoming smarter through the integration of IoT, Internet of Things, AI, artificial intelligence, and wireless connectivity, the BCM does more than just reduce wiring. It integrates intelligent features such as sensor-based automated lighting, speed-sensing door locks, and power management to prevent battery drain. This lecture provides a systematic, in-depth, yet accessible overview of the BCM, ideal for students and automotive enthusiasts looking to understand the brain behind everyday vehicle conveniences. We will explore fundamental concepts, mounting locations, its role in overall EE architecture, key functions with real-world examples, network communication, diagnostic methods, and its historical evolution. Based on research from industry leaders like Bosch, Continental, and Delphi, as well as SAE International Standards, this article emphasizes practical applications to help readers apply theory to vehicle maintenance. 2. History and evolution of the BCM. The history of the BCM is inextricably linked to the evolution of automotive electronics, moving from simple mechanical systems, relying on relays and manual switches, to today's intelligent modules capable of real-time data processing. Before the 1970s, body electronics consisted of basic circuits using hundreds of feet of wiring to connect switches directly to components like headlights or wipers. This approach added 110 to 220 pounds, 50 to 100 kilograms, to the vehicle's weight and was prone to failure due to vibration and oxidation, leading to high repair costs and low reliability in classic American cars like the Ford Mustang or Chevrolet Impala. A major shift occurred in the late 1970s and early 1980s when U.S. manufacturers like GM and Chrysler introduced the first electronic control systems to meet EPA emissions and safety regulations. According to GM Historical Archives, this period saw the birth of basic automotive networks and the use of multiple onboard computers. For instance, the 1979 Cadillac Seville and 1980 Oldsmobile Toronado began using individual control modules for lighting and locks, marking the inception of the BCM concept. These early units utilized multiplexing, allowing a single wire to transmit multiple signals, which reduced weight and improved fuel efficiency by 5 to 10%. The 1990s saw the BCM flourish with the adoption of the CAN, Controller Area Network Bus, developed by Bosch in 1986. By the mid-90s, the BCM became a central hub for power windows, auto lighting, and basic anti-theft systems. This transition reduced vehicle weight by up to 30% and enabled fault diagnosis via the OBD, onboard diagnostics port. By the 2000s, the BCM was upgraded with the LIN, Local Interconnect Network, for simpler components, and FlexRay for high-speed luxury applications. This era introduced smart energy management and sensor-based automation, seen in the 2003 Toyota Prius and 2006 Honda Civic. According to a 2023 report by Precedence Research, the global BCM market is projected to reach approximately $35.84 billion by 2025, driven by the rise of EVs and hybrids. Today, BCMs integrate AI and OTA, over-the-air software updates. Manufacturers like Tesla and Hyundai lead this charge. allowing vehicles to upgrade functions without a trip to the garage. By 2035, the market is expected to hit $48.15 billion as 5G and autonomous driving become standard. 3. Concept and location. The BCM is a central microcontroller designed to receive signals from switches and sensors, process them via pre-programmed logic, and issue commands to actuators, relays, motors, lights, or communicate with other ECUs via the vehicle network. Key components: microprocessor, MCU, typically 32-bit or 64-bit chips, for example, TIMSP430 or NXPS32K, capable of multitasking and EMI resistance. Memory, ROM 512 kilobytes to 2 megabytes for firmware, and RAM, approximately 128 kilobytes for temporary data and DTCs, diagnostic trouble codes. Power circuits, DC converters that stabilize 12 volts or 48 volts battery power. Communication interfaces, CAN up to 1 Mbps, LIN 20 kbps, or FlexRay 10 Mbps. Typical mounting locations: under the dashboard, driver or passenger side for easy access, for example, 2023 Toyota Camry. Integrated with the fuse box, typically in the cabin or engine bay, for example, Ford F-150. Kick panels, pillars, to minimize wiring runs to door and steering column components. 4. Roll-in EE architecture. Modern vehicles use domain-based architecture to increase modularity. Powertrain domain, PCM, ECM, engine and transmission management. Safety domain, ABS, ESC airbag, high priority, high-speed response. Body domain, BCM, comfort, lighting, and user interaction. Infotainment domain, screens, GPS, and connectivity. The BCM acts as the gateway for the body domain. For example, on a Honda CR-V, when you flip the headlight switch, the signal is sent to the BCM. The BCM checks conditions. Is it dark? Is the car moving? Before activating the lights via MOSFET and notifying the instrument cluster to display the icon. 5. Key functions lighting control. Manages high-low beams. Turn signals 60 to 120 flashes min. And follow me home delayed lighting. Uses PWM, pulse width modulation, for dimming. Access and locking. Handles central locking. Remote keyless entry, RKE, with rolling codes and speed sensing auto lock. Includes anti-pinch protection for windows, reversing if resistance greater than 20% or 5N is detected. Wiper washer systems. Processes rain sensor data to adjust wiper speed 30 to 90 cycles per minute automatically. Security. Manages the alarm system and coordinates with the immobilizer to verify RFID keys before allowing the engine to start. Power management. Enters sleep mode, drawing 50 milliamperes to prevent battery discharge. 6. Network communication. The BCM communicates via CAN for high-priority data and LIN for low-cost peripheral control, mirrors, switches. In a crash, the SRS airbag module sends a CAN signal to the BCM to automatically unlock doors and activate hazard lights. Signs of BCM failure. Because the BCM controls multiple systems, symptoms often appear random: erratic lighting behavior, flickering or staying on, unresponsive door locks or remote key fobs, power windows failing to move or reversing without cause, intermittent wiper operation, no key detected, errors or failure to crank, parasitic battery drain, module fails to enter sleep mode. 8. Causes of failure: water ingress, leakage from windshields or high-pressure washes causing corrosion, short circuits, improper aftermarket accessory installation, for example, dash cams, voltage spikes, incorrect jump starting or battery replacement procedures, software glitches, failed OTA updates or firmware bugs. 9. Diagnostics and repair. Diagnosis requires professional scan tools, for example, Automaxis. Launch X431 to read BCM-specific DTCs like B1000. Software reflashing, using OEM tools like Toyota Camry to update firmware. Hardware repair, replacing blown MOSFETs or relays, requires microsoldering. Replacement. New units often cost $200, $800. Replacement requires programming the VANG and syncing with the immobilizer keys, a process taking 1 to 2 hours. 10. Notable BCM characteristics by vehicle model. While BCM architecture varies by manufacturer, the following examples highlight how the module is implemented in popular global and regional models. Toyota Vios. The BCM is typically integrated into the main junction box, fuse box. It focuses on essential reliability, managing exterior lighting, central locking, and the immobilizer. It features a high-efficiency rapid sleep mode to maximize battery life during long periods of inactivity. Honda City. This module features advanced cabin comfort logic, supporting one-touch power windows with anti-pinch protection. It also integrates rain sensor data and adjusts interior ambient lighting brightness based on GP's sensed time data. Ford Ranger. The BCM in this platform is highly robust, managing automatic wipers and follow-me home lighting delays. It plays a critical role in coordinating body-related 4x4 functions and is deeply integrated with the vehicle's 360-degree camera system for perimeter monitoring. Hyundai Accent. Focused on energy efficiency and urban safety, this BCM manages speed sensing, auto locks, and smart power distribution. On higher trims, it handles sophisticated smart key authentication, including biometric or fingerprint verification in some markets. Mazda CX-5. Known for deep integration with Mazda's security and convenience suite, this BCM supports automated sunroof closure when rain is detected and manages adaptive LED headlights that adjust their beam pattern based on steering and speed. 11. Conclusion. The BCM has evolved from a simple relay replacement into a sophisticated brain essential for the EV and autonomous driving era. As we move through 2026, its role will only grow with 5G connectivity and advanced driver assistance systems, ADAS. For technicians and engineers, mastering BCM logic is no longer optional. It is a foundational requirement for maintaining the safety and comfort of the modern automobile.